Hello everyone, my name is Nikki Arendse. I'm a postdoc at the Oscar Klein Center at Stockholm University, and I'd like to talk about lens supernova science with the Rubin Observatory. So first of all, a big shout out to the organizers of this BOOM conference, which has been truly amazing to come together and discuss transient science. And I would like to focus on a combination of transients and gravitational lensing, so strongly lensed supernovae. And type 1a supernova have already been used extensively in cosmology to map out the shape of the expansion history because of their standard candle nature. And gravitational lensing is useful because it allows us to calculate the matter distribution in the universe and absolute distances. And when these two things are combined together into lensed supernovae, they're especially powerful. And hopefully they will help us to resolve one of the biggest mysteries in current day cosmology, which is the Hubble tension. So let me briefly give you an overview of this talk. So first, as a background, we'll discuss the Hubble tension and then how time delay cosmography might be able to shed some light on this. And then we'll look at all the lensed supernovae that have been discovered so far. Then I'll talk about a project that I'm working on within the Dark Energy Science Collaboration, or DESC, which has the aim to infer the Hubble constant from lensed supernova images using machine learning. And within this project, we'll take a deeper look at the effects of microlensing on the population of lensed supernovae that we'll discover with Rubin. And then I'd like to introduce a joint effort of the Strong Lensing and the Dark Energy Science Collaboration, which is the Lensed Supernova Simulation Team. So as I said, there's a big problem in cosmology related to the value of the Hubble constant, or the present-day expansion rate of the universe. So here we see an outline of the timeline of the universe, where we have the Big Bang on the right, and then the CMB, the evolution of structures, and the present day on the left. Now, if we want to understand the evolution of the universe and make predictions about its future, we need to know how much it has expanded at every point in time. And this is mapped out, as I said, by type 1a supernovae. Now, the Hubble constant is the normalization of this expansion history. So we need it in order to calculate the age of the universe and also to calibrate distances to astrophysical objects. Now, there's two different ways how we can measure the Hubble constant. The first one uses the first light we can see, so the cosmic microwave background radiation, in order to infer parameters at recombination when the light was released. And then if we want to know the present day expansion rate of the universe, we have to extrapolate these parameters to the present time using a cosmological model, for which we use the lambda CDM model. The second approach uses local astrophysical sources and then relates their distances and redshifts in order to get the Hubble constant. So this I will refer to as the local method. And it doesn't require a cosmological model because the data points already map out the shape of the expansion history. But what is often used here is a distance ladder. So this is a multi-step approach to use the low redshift calibration of nearby astrophysical sources to relate it to the high redshift supernovae in the Hubble flow. And if we look at the results from each of these methods, then the CMB method, as carried out by the Planck team, obtains a Hubble constant of 67.4, while local measurements by the Schu's team using Cepheids and type 1a supernovae get a higher value of 73. So these two measurements are now in 5 sigma tension with each other. And this discrepancy is really a big open problem in cosmology, because it also calls into question the lambda CDM model that goes into the CMB analysis. But in order to assess whether this is really a tension between the early and the late universe, it's important to have some more independent measurements of the Hubble constant. And ideally, these measurements would not depend on the distance ladder, but instead have a direct distance measurement to high redshift objects. And this is then where gravitational lensing and time delay cosmography comes in. So how does this work? Well, we have an observer that looks out into the universe and sees a massive galaxy or cluster with a distant source behind it. Now, the light from this source can be bent and magnified by the gravitational potential of the lens galaxy, so multiple light rays can reach us, and in this case we see two images of the very same object. Now, if this source is also a transient or a variable source, such as a supernova or a quasar, then the variations in brightness of this object will arrive at the images at different moments, because they travel a different path to each image and they're also affected by the gravitational potential of the lens galaxy in a different way. And with very extensive monitoring campaigns for quasars, we can actually observe the differences between these variations in the images and then determine the time delay. And this time delay scales with the gravitational potential of the lens galaxy and a ratio between distances between the observer, the lens, and the source, which is called the time delay distance. So since this time delay distance is an absolute distance, it scales inversely with the Hubble constant. And gravitationally lensed quasars have already been used successfully to determine the Hubble constant, as you can see here by the Holy Cow collaboration. And they've used 6 lensed quasar systems to get precise measurement of H0. And there are still some open questions about the mass profile of the lensed galaxies and anisotropies within it, which will be solved with more data in the future and especially spatially resolved kinematics. So quasars have been very useful for this purpose, but when this idea of inferring the Hubble constant from time delays was originally proposed in 1964 by the Norwegian astrophysicist Refsdal, he actually envisioned it with lensed supernovae. And this can have several advantages. So especially when the supernova behind the lensed galaxy is a type 1a, then this will give you additional constraints on the absolute magnification, which can be helpful in breaking the mass sheet degeneracy. Also, it will teach us a lot about high redshift supernova physics if we discover these objects, and they can be used to map out the dark matter distribution in the lensed galaxy. So after this idea was proposed by Refsdal, it would take another 50 years before the first example of multiply image lensed supernova was observed. So here this is supernova Refsdal, which was named in honor of the Norwegian physicist who sadly died 5 years before this. And this is a very special example. It's a supernova lensed by a galaxy cluster, and here actually the host galaxy of the supernova has also been lensed and imaged multiple times. So you can see it in this image in 1.3, 1.2 and 1.1, the same galaxy. And then if we zoom in on 1.1, then a supernova went off in this galaxy, which was then also lensed by part of the cluster, resulting in 4 images of the supernova here. But of course, the same supernova should also appear in the other images of the galaxy, because it's the same one. And then when this team constructed the lens model of the galaxy cluster, which you can see here in white lines are the critical curves, they predicted that the supernova would have already gone off in 1.3 earlier, but we missed it. But they predicted that it would appear within a year in image 1.2. So they were ready with follow-up observations, and exactly as predicted, the supernova appeared there. So this was really a great test of the lens models, and it also allowed for a precise measurement of the time delay, which can then result in a 6% measurement of H0 from only this system. So it's quite extraordinary. And there has been a discovery of another lens supernova by galaxy cluster called Supernova Requiem, for which Justin Perel is going to talk about more, and also talk more about the differences between lens supernovae clusters and normal galaxies. Because so far there have been a few lens supernovae discovered in galaxy clusters, but actually the expectation would be that we would find more behind normal galaxies, elliptical galaxies. And of this we only have one example so far, which is IPTF 16GU. So this is a type 1a supernova that was lensed by a normal elliptical galaxy discovered in the IPTF transient survey. And this one stood out because it was exceptionally bright for its redshift. So then when they conducted follow-up observations, they discovered that indeed it was a lens supernova. And the configuration, as you can see, is quite symmetric here. This also leads to very short time delays of the order of a day, which makes it pretty much impossible to get an accurate measurement of the Hubble constant. But this system is still very interesting in other ways. So some of the properties are a bit surprising. If you have such a symmetric lens system as this one, you would actually expect that most of the images are very comparable in brightness. But this is not the case, and especially this image over here is much brighter than the rest, which is hard to explain with the macro-lens models. Another thing is that the magnification of this lens system is quite high, so around 70 for the total magnification, which is definitely on the tail end of what we would expect. But of course this is also a selection effect which made it a lot easier to discover it. So there have been some speculations that these different flux ratios between the images and the high magnification in total could be explained by microlensing. And I will get back to this a bit later in the talk as well. But of course it's very difficult to draw conclusions from only one object, and we really need a larger sample in order to say more about this. So why has it been so difficult to discover more of these supernovae lensed by normal galaxies, since we only have one? Well, this is because in the current transient surveys, such as ZTF or the Pan-STARRS telescope, the majority of the lens supernovae that would be discovered would actually be unresolved. So you would not be able to see the multiple images. And 16 GU, when it was discovered in IPTF, actually looked like this. So it was not very clear that this was a lens supernova. And only because it was so bright, they did follow-up observations, and then you can really see the characteristic features of the lens supernova. So this means that currently we're in a very hard position where we have to look for a needle in the haystack from very subtle signatures and also rely on photometric redshift estimates because we don't have resources to follow every source up spectroscopically. So this is a bit of a difficult game, and if we manage to do it, we could discover like at most a handful of lens supernovae in the current surveys. But these numbers and odds are about to change drastically with the advance of the next generation telescopes, such as the Vera-Rubin Observatory and the Roman Space Telescope. So here are some predictions for Rubin, or LSST. How many lens supernovae will be discovered in 1 year is around like 91 A's and 250 Gorka-Lab supernovae. So this is such an increase in numbers of a few orders of magnitudes, so it's quite exciting. But of course it also brings along different challenges. So first of all, we need to be able to look for these supernovae in very big volumes of data, of several terabytes each night. And we have to do this while we only have a very small set of actually observed supernovae, lens supernovae. So this means that simulations will be crucial in order to help us determine what we have to look for in the real data. And another thing is that LSST is usually proposed as a discovery machine. So it will observe and discover some of the lens supernovae, and then we will do high resolution follow-up observations to actually get the cosmological constraints. However, I was also interested in the question whether if we only use LSST data, if we could already be able to infer the Hubble constant from the lens supernovae that would be discovered in it. Since it's going to discover so many of them, we might be able to combine all of this data and still get a useful estimate of H0. So this led to the desk project that I will talk about more now, which is inferring the Hubble constant from lens supernovae in LSST using spatial-temporal neural networks. And this project, I'm working on it with multiple people. I'd just like to highlight here Radek Wojtek and Dugas Kaudiramena from the University of Copenhagen, with whom I started it. So I will just unpack this title in two different parts, first focusing on the lens supernova part. So in order to simulate lens supernovae according to what LSST is going to observe, here you can see the configuration, and the few things we need are of course the redshift distributions of the lens galaxies and the supernovae, and then the image properties of LSST and a realistic cadence. And for the lens galaxies, we assume a power law elliptical lens model which has 4 free parameters: the Einstein radius, the power law slope, and the 2 ellipticity components. And then we also include microlensing, which I will come back to in more detail later on in the talk. And for the supernovae, we only focus on type 1a supernovae now at the moment, for which we simulate the light curves with SN Cosmo, drawing parameters from stretch and color distributions for type 1a supernovae. So when we put all of this together, then this is what our data output looks like for one lens supernova system. So here you see the time evolution of the lens supernova in difference images, because for these images we only simulate the supernova, so not the lens and the host galaxies. And this will also be one data product of LSST. And then we combine these images into a cube by stacking all the observations behind each other, and this will be the input for our neural network. So going back to the title and now focusing on the spatial-temporal neural network part. So in our case, this machine learning model consists of a 3D convolutional neural network, where the 2 dimensions are sensitive to the features in the images, and then the 3rd dimension to the temporal dimension of it. So the input that I showed before is then going first through the convolutional layers, and then some fully connected layers to finally give multiple outputs. And the outputs we have here are the lens parameters, the positions of the images and the source, and also the time delay between the images. Now these are then combined together analytically to get an estimate of the time delay distance, and finally the Hubble constant. So for this last step, to get the Hubble constant, we need to assume a cosmological model for which we use lambda CDM, and we also input the redshifts of the lens and the source galaxies. So we assume that after the supernova has faded away, we can conduct follow-up observations of the lens and the host galaxy to get spectroscopic redshifts. Now this pipeline so far would only provide us with point estimates of the Hubble constant, but of course we are actually interested in the full posteriors to get the final uncertainty on H0. So to do this we use a simulation-based inference framework to convert these point estimates into posteriors. And simulation-based inference is also sometimes referred to as likelihood-free inference or implicit likelihood inference. So it has many names, but the idea here is that the shape of the likelihood is not available analytically, so it needs to be approximated, usually by simulations. And how we approximate it is by looking at the scatter between the predicted and the ground truth values of the Hubble constant. So a large scatter here would result in broad posteriors and little scatter in narrow ones. And if we predict for one lens system a certain value of H0, we would get a posterior by slicing this distribution at the predicted value of H0, so resulting in different posteriors for each value. And in order to do the density estimation, I'm working together with Justin Elsing, and we're using neural density estimators, and more specifically Gaussian mixture models. So this is a sum of different Gaussians that can be quite flexible to approximate the shape of these posteriors. So let's have a look at what these posteriors look like for multiple different lens systems that have been simulated, all with a ground truth value of 70. So you see that each posterior by itself really does not have a lot of constraining power, but if we combine all of them together, there really is strength in numbers, and they do converge to a better estimate of H0. Now, in order to get an estimate for the precision that we expect, for example, within 1 year of LSST observations, we use the numbers from Radek Wojtek et al., where they predict that for type 1a supernovae, there will be around 34 doubles, which are lens supernovae with 2 images, and 9 quads, which are supernovae with 4 lens images. So these will be discovered yearly in LSST using the image multiplicity method. So this means with the image multiplicity method that they are discovered because they have multiple images, so the images are also resolved here, which makes it easier for us to measure the time delays. However, I don't have a final estimate yet, because for the simulation, now it's only in the I band, and we're also going to include simulations for multiple bands using a simulated cadence by Katerina Alves, and also include microlensing effects by Simon Huber. But one interesting thing to look at here as well is the uncertainty budget. So how much does each of the parameters contribute to the final uncertainty in H0? And here you can see that for each parameter for doubles and quads. And you see that for doubles, the main uncertainty is caused by the time delay and the position of the source. So when you only have 2 images, it's a bit more difficult to constrain the lens model and the configuration of the source behind the lens galaxy. For quads, the main uncertainty is the time delay and the position of the images. So here you have 4 images, which gives you better constraints on the source position, but because the images are usually quite close together and some of them are also quite faint, it can be hard to distinguish the different images from each other. So knowledge about this will be quite useful for follow-up observations to know what to target in order to improve our estimates. And here you see the residual scatter again as a function of time delay, and here you see that if we go to lens systems that have a short time delay, then the time delay becomes the dominant source of uncertainty for both of these doubles and quad systems. So this is the blue line, which really increases for the low time delays. And this is because the shorter the time delay gets, the more difficult it is to precisely measure it. So now let's talk about microlensing. So as I said, these are additional magnification contributions from stars and substructure in the lens galaxy. And for lens supernovae, since the images are typically a bit closer to the lens galaxy, this can have an important effect. And that's why we also wanted to investigate how it would impact our results. So here we see an image of a lens galaxy with 2 supernova images. And in order to calculate the microlensing contributions for each position around the images, there are 3 important parameters. So the first one is kappa, the convergence, and this is the projected surface mass density, which results in an isotropic magnification. And then we have gamma, which is the shear, and this results in distortion or stretching of the images. Then S is the smooth matter fraction, so the fraction of dark matter to stellar matter. And for the image that's located closest to the lens galaxy, the convergence and the shear are both high, and the smooth matter fraction is low because there's more stellar matter compared to dark matter. So if we take this into account, then we can calculate for each of these substructure the microacoustics that it will create. So these are individual additional magnifications due to all these stars. And as the supernova photosphere will expand, it can cross some of the microacoustics, which then results in an additional magnification. So we're working together with Simon Huber, who has a pipeline for microlensing simulations. So he computes the microacoustics and then the expanding supernova to calculate all the contributions. However, this is quite computationally expensive. And if we want to simulate a training set of like 50,000 objects, it's not really feasible. That's why we're using an approximate method where we selected 16 combinations of kappa, gamma, and S that occur often in our simulations, so they're representative of our data. And for each of these combinations, Simon calculated a microlensing magnification map, and then put expanding supernovae in 10,000 locations to capture the stochastic behavior of microlensing. So for each of these, if we have a lens supernova, then we sample the combination of kappa, gamma, S that is closest to it, and we pick one random location in the magnification map. And then we add the microlensing magnification to the normal macrolensing magnification. So here you can see a result of a light curve where the dashed lines is the macrolensing, so without any microlensing taken into account, and the solid lines are what you get when we add a random microlensing realization. So for this system, it would result in both of the images being a bit fainter than without microlensing. And it turns out that this is quite often the case, actually, that the images get a bit fainter. So here we can see the magnification distribution, where the black line corresponds to the macrolensing, so without any microlensing, and the blue distribution is coming from different microlensing realizations. So as you can see in this tail end, there are some systems that are magnified a lot more than without microlensing, but the majority of the systems is a bit fainter. And you can also see this in the median. So when we simulate lots of different light curves, as you can see on the right, we have the black line, which is the supernova light curve without any microlensing. And then the green lines correspond to different realizations of microlensing. And as you can see, the majority of them is actually a bit fainter. So this is an important effect because it can actually impact how many lens supernovae we will discover, since many of them that are predicted to be observed with LSST are sort of on the threshold of being observed. And if they become a little bit fainter, then we can already miss them. So with my simulations, I just ran a rough estimate and found that only 75% of the supernovae that we predicted to observe would still be observable, which is a bit concerning. So it could potentially decrease our sample size quite a bit. But there are also a small number of lens supernovae which will be highly magnified. So these are the ones with the larger light curves over here. And this can be quite useful because they will be very easy to observe and also very helpful for cosmology if they're a lot brighter because we can see more of their light curves. So this leads us back to 16 GeU, which we can expect that maybe this was one of the ones that was highly, that some of the images were highly magnified due to microlensing, which would expect why it was so bright that we could observe it, and also why the flux ratio of the images was more different than you would expect for such a symmetric system. And another effect that can occur due to microlensing is that the light curves get a bit distorted from the original shape. And you can see one example over here that doesn't follow the original shape so well. But for the majority of the light curves, they do seem to obtain mostly the same shape, which makes our life a bit easier if we want to determine time delays. So to conclude, lens supernovae are a promising new probe for independent measurements of the Hubble constant. And since our lens supernova observed sample will be very small for the next coming years, simulations are crucial to obtain new insights into the expected precision of cosmological analysis and the dominant sources of uncertainty. So in our simulations, we found that the time delays and the source position for doubles or the image positions for quads are the main sources of uncertainty. And this can then be useful for follow-up observations because we know which parameters to focus on and what data to get. It can also give us new insights into the effects of microlensing. So we found here that a few lens supernovae will be highly magnified, however the majority of them will be fainter, which will lead us to miss out on a few of them. And of course we need simulations to test and validate our lens supernova finders. So because of this, there's a new effort with the strong lensing and the dark energy science collaboration together, which is the Lens Supernova team. So this consists of Justin Perel, Suhail Dawan, Brian Nord, and myself, and we work within the strong lensing pipeline that is led by Remy Joseph in order to get realistic lens supernova simulations. So our main objectives are, first of all, to simulate realistic lens supernovae, and then to inject them into the DC2, which is data challenge 2, so a large simulation set of LSST data, and eventually also in real LSST data. And then we can use this to create large training sets to train our machine learning models and test out our lens finders and cosmo-analysis methods. So hopefully with all these methods, we will be ready for the first lens supernovae with Ruben, which will undoubtedly teach us a lot more about high redshift supernovae physics, cosmology, and the Hubble tension. Thank you.